So the table, number 6 for the part 2, looked like this, right? So you realize that if there were 2 fans, right, and each one gave a force of 4 newtons, that it was a total of 8 newtons, right? 1 fan was 4, and then of course 3 fans was 12 newtons. So then it asked you to multiply mass times acceleration. And you probably found that you got a number close to 8, a number close to 4, and then a number close to 12. So what did you notice about this column and that column? What did you notice, Maddie? Yep, the same. Okay, why? Why are they basically the same? Isaiah?
Because the equation for force is mass times acceleration.
Okay, by the way, it is May the 4th. So May the 4th be with you.
No.
I said it. You're going to be all right. Sometimes you will see the may the mass times acceleration be with you. That's why. All right? So when we say F equals ma, right, we're talking about the net force is equal to the mass times acceleration. And that is just an algebraic manipulation of Newton's second law. Okay? So it actually showed that F net was equal to ma. That's what this experiment showed. Yeah? Okay. There were a few comprehension questions at the end that I want to make sure we talk about on the tricky side. Number 8 shows us a graph of v versus t. And it asks you what the initial velocity was. Who knows the answer to that? Vanessa?
0.5.
How did you get 0.5?
Because the line starts like the y-axis, and the y-axis it starts at 0.5.
Okay, good. So we're looking at this point, right? And you can see this is 2, that's 1, that's 0, so it was 0.5. So when we're talking about initial velocity, the initial velocity means the v at t equals 0, right? At the time of 0. That's what initial velocity means. Cool. Number 9 was a little trickier. Let's talk for a second about what we're even looking at. We have a graph of acceleration versus time. What information do you see on this graph? It is a constant acceleration of what value? 0.4. So it has an acceleration of 0.4 meters per second squared. And it has that like forever, right? Constant. So now it says if a second block is added to the cart. What does that mean? What are we doing? What's that? Why do you think we're slowing it down? Okay, so if a second block is added to the cart, that means that the mass increases, right? Can I get some vigorous nods? Okay, well, when we look at Newton's second law, if the mass increases and the net force stays the same, what happens to the acceleration? It should go down. Remember, A is inversely proportional to mass, right? So it started at 0.4 meters per second squared. So what is it going to do when we increase the mass? It's going to go down. So what is the answer? So if it started at 0.4 meters per second squared and it goes down, so 0 would be if there were no net force. It will be 0.27 meters per second squared because it has to be lower than 0.4, but it can't be 0 because 0 would mean that there's no net force. Does that make sense? Okay. All right, last one, number 10. Let's again look at a velocity versus time graph. What information can you get from a velocity versus time graph? Isaiah?
the initial velocity
You can. There's the initial velocity.
and
What-
the amount of time it takes for something to get to the end.
Okay. Well, there's an assumption that there's an end there. But what other information? Anna? Yes, the slope is equal to the acceleration, right? That's super important. So here it says we've got 2 fans, and then we turn on the 3rd fan. All 3 fans means what? What did we increase?
Mass.
We did not increase the mass because the fan was there before.
Or you increase force.
You increased the force. So the net force increased. So if the net force increased, then what's that going to do to the acceleration? It's going to increase. So now the question is, how can I tell that I have a bigger acceleration by looking at a graph? What is a bigger acceleration?
Would it be more inclined?
What is it?
Would it be more inclined?
Yes, steeper slope, right? A steeper slope means a bigger acceleration. Does everybody get that? 2 of you? Okay, 3? Cool. So now we look at these graphs and we're like, okay, this guy went up here. So I'm going to draw this original one. So which one was steeper? D. Okay. All right. How's it feel? Okay? Fantastic. Okay, so one of the interesting things that you might have noticed are the units. When you did the table, it asked you to calculate mass times acceleration. And it's possible you didn't quite know what to do with those units, so I want to talk about that now. What is the SI unit for force? It is. Okay, but it also said that F equals MA, right? So hold on. To be dramatic about it, let's make sure we are in a different color. Okay. You said the force unit is Newton? Okay. What's the mass unit? Kilograms. What about the acceleration?
Meters per second squared.
Meters per second squared. Guess what? That Newton has been a kilogram meter per second squared that whole time. It's been masquerading as an innocent unit,
Isn't that, wait,
but it's actually a compound unit.
yeah.
Okay, so it means it's made up of kilograms, meters, and seconds. Do you guys remember when we first introduced SI? I called it the MKS system. Do you remember me saying that?
Nope.
Awesome.
What was this like the beginning?
At the beginning of the year when you didn't listen at all? Mm-hmm.
Like 3 months ago when I didn't listen at all.
Yeah, fair. Okay. Is it what? S squared on the bottom? Yeah. Right, like meters per second squared? So what do you think MKS stands for? That's exactly right. Meters, kilograms, and seconds. So every unit that we use in physics, even if we give it a special name like Newton, is actually made up of meters, kilograms, seconds, and for temperature is Kelvin, and then also amperes. Do you know what an ampere is?
Isn't that an electrical unit?
It is. It's electrical current, an amp, right? You might have heard of amps? okay? But every unit, even if it has a special name, is actually made up of these other units. Have we used any other units in this class?
No.
We totally have.
You mean overall?
Yeah, like what other units have you heard of? So those are imperial, right?
Wait,
Okay. But what other SI units have we seen?
Oh, the gravity.
What was gravity?
F low G.
F sub g was a force due to gravity, which was in newtons. Little g was in newtons per kilogram. Hey guys, what's a newton per kilogram?
I don't know.
Hold on. It's a kilogram meter per second squared over a kilogram. Oh my goodness. It's a meter per second squared.
This is,
You are going to see this.
where did the Newton go?
The Newton is that.
N.
There's your Newton,
Oh.
right?
You should have told us this before you made us do the whole thing where we had to break down each thing and then cross them out because
Well, no,
there's
that
still
this
a
is
Newton there and there's still a kilogram there.
no, I'm showing you that a Newton per kilogram is equivalent to a meter per second squared. That's going to be very interesting in 2 more classes when we start talking about free fall. So get ready for that. But what other units? What'd you say?
You're the best.
Yep. What other units have we seen this year? Okay, so those are also thingamajiggies. Yes, Malia? What? Joules. What's a joule? Yes, it's a vaping device that we don't advocate. Okay, so joule is, do you guys remember? It was from work, right? Which was a force times a distance. So a joule was a Newton times a meter, right?
Yeah.
And a Newton is a kilogram meter per second squared times another meter. Oh my gosh. So it's just messy. You don't need to know this, but you don't need to know that a joule is a kilogram meter per squared per second squared. Okay?
Stop.
However, the point is that things that you have seen before, which have these nice tidy names, right, are actually made of kilograms, meters, and seconds. This is important because when we do math with it, right, the units have to work out. So when we say A equals net force over mass, the units need to work out, don't they? They do. What should your acceleration be? What should acceleration have units of? Meters per second squared, right? Okay. And our net force is going to be in newtons, so that's going to be a newton. And then a mass is a kilogram. And so there's that meters per second squared is Newton per kilogram. So that's a relationship. And that's because Newton is, right, we're just kind of going back and forth. Whee! Okay, all of this unit math. So here's the deal. If you can follow the unit math, that's great. If you can't, just trust that your equations will work out and that the units should work out. But I wanted to show you that we're not doing anything tricky here. We're not doing anything like magical by saying that kilogram meter per second squared is magically a Newton. That's how it's defined. Yes, Isaiah.
So does this technically mean that you can find the acceleration from kgm over s squared?
kgm over s squared is a unit for a force.
But can you technically find the acceleration from that?
If you
Or
know,
kgm over s squared over kg.
right, so what you're saying is if you know the net force and you know the mass, can you get the acceleration? Yes, that is Newton's second law, my dear.
Yes, I know this.
Okay.
But because you just showed all of that equals that, can you not just find the acceleration for doing kgm over s?
Well, these are just the units. They're not the numbers.
But I know, but if they were numbers, could you technically still find the acceleration?
Okay, so the numbers go in front of the units, right? So I'm going to pause. You're going to hold the seesaw where something is held constant. So if I say, if the net force is constant and I increase the mass, what happens to the acceleration?
It goes down.
It goes down. What happens if I hold the net force constant and I decrease the mass? Acceleration goes up.
Oh, wait.
Do you see?
Oops.
Okay. So I'll write this down in a second. Hold on. But the idea is that if you hold the net force constant and you increase the mass, right? If m goes up, a goes down. If m goes down, a goes up. That is, a is inversely proportional to mass, right? We've said this a couple times now about them being inversely proportional. Yes? We're going to now, what if we hold the mass constant? Can you try it? What happens if I increase the net force?
They're directly proportional.
Aha. Right? If you hold that mass and that net force goes up, then the acceleration also goes up. If you hold the mass and the net force goes down, the acceleration also goes down. Does that make sense?
Yes.
And that's because they are directly proportional.
Yeah.
Does anybody remember, we talked briefly about what net force is. Does anybody know? Net force.
Isn't it what's being put on the object to make it move? Or what is moving the object?
So, right, it's like a force, but it's not just a force. The word net in English also means the same kind of thing. Yeah? The overall, hey guys, right? The overall is the sum of all the forces. Does that ring a bell? Okay. The sum of all the forces on an object. Oops.
Oh, so like
So when we were talking before about balanced versus unbalanced, we were really talking about their net force. Okay, so you remember when I was like, someone's pulling me this way, or if someone's pulling me this way, right? Then we had talked about that idea of balanced and unbalanced. We're really talking about the net force. So what do you think is true for a balanced situation? Yes, Siri? So equal force on both sides, but you can also have like lots of different sides. But what do you think about the total value of the net force? It's 0, that's right. The net force is 0. And what do you think unbalanced means? Joseph? Exactly, it's not 0. Okay? So every time we say balanced and unbalanced, I want you to make sure you remember this term net force. Okay? I want to focus a little bit closer in on the balanced situation. Because the balanced situation where net force is 0, there's another name for that. Does anybody know the name for a situation that where the net force is 0? Anybody know?
equilibrium.
It is equilibrium. It is called mechanical equilibrium. Look at the word equilibrium. You see the word equal in it? You see the brium? Yeah, that's super useful, that part. Okay, mostly the equal, right? So it's a mechanical equilibrium. Do you remember any of the situations we talked about right at the beginning of this unit where we talked about mechanical equilibrium? Yeah?
The no acceleration, no velocity.
Yes, good. We had like 2 situations, right? We had like a book sitting on a table and it had equal forces, right? And I don't know, let's put some numbers to it. Maybe the book weighed 10 newtons and then the table was pushing up 10 newtons. It was just at rest, right? And remember, we also had a bowling ball. Bowling ball was heavier. Maybe it was 50 newtons. And the table or floor was pushing up on it, right? But it was moving, right?
In equilibrium.
But what was it doing? What kind of movement?
It was just
It was just chilling, going forward at a constant velocity. Good. So,
something is at a constant velocity, is it also in equilibrium?
yes, if something is at a constant velocity, this is also in equilibrium. So, V equals 0 or V not equal 0, right? Cool. If something's at rest, V equals 0. Something's going constant velocity, V's not 0. Everybody cool with that? This, what's wrong? Moving? Sure. I know, you trust me. It says moving. All right, there are words that we use to describe these two kinds of equilibrium. And let's see, you learned something in gym class about stretching that talked about if you're stretching and you're still, or if you're stretching and you're moving. Yes, dynamic. Which one of these is dynamic equilibrium? Bowling ball. Dynamic,
I was thinking, why do you have to say nomadic?
not nomadic. Static. So static equilibrium is where F net is 0 and V is 0. Dynamic equilibrium is where F net is 0, but the velocity is not 0. But in all these cases, in all two of these cases, all of them, what is the acceleration? 0, right? If F net is 0, acceleration is 0. I want you to marry those two ideas in your head, right? If you see F net is 0, I want you to think acceleration 0. Acceleration 0, constant velocity. I want that to be sort of that link. Does that make sense?